Okay, this is the second problem with Chapter 5, which is thermochemistry. Okay, so this is dealing with a concept called Hess's law. Given the data below, so we have three different chemical reactions and their delta H values. Calculate delta H for the reaction of ethylene with F2, fluorine gas. So the idea behind Hess's law is that we cannot measure the delta H value directly for the reaction of the ethylene with the F2. So since we cannot measure that value directly, if we have simpler component reactions, we can measure that value. So because we have these reactions and their delta H values are known, we can manipulate them, and we can multiply them by numbers. We can simply reverse them. We can do whatever we need to do to get these three sub-reactions or component reactions to match the overall reaction. Okay, so basically, I always like to start out with the most unique element. So, what is unique to this reaction? So I'm looking at the C2H4, the ethylene, and I'm looking at the three subcomponents, and the only equation in which that appears is the third one. And I noticed too that the ethylene in the subcomponent reaction is considered a product, but we need to get it to be on the reactant side. So as you might have guessed, we need to inverse this third reaction. And that way, when we add, we're going to have to add all these up at some point to equal the overall reaction. When we add them, we need the C2H4 to be a reactant. So let's write our first component reaction. Okay. Okay, so that's our first component, and notice it is inverted. The reactants are products, and the products are reactants. So that allows us to take its delta H value and invert the sign. Okay, so you'll see what I mean when we go to add all the reactions in the end. So this is our first. So we do have that in the right spot. As you can see, it is a reactant. But that's all we have so far. So let's look at our next reaction. So we look at the HF, the hydrofluoric acid, and we notice that there are there are four in the overall reaction. There's four in the product side. So looking at our first component reaction, the HF is on the correct side. It is a product. However, we need to have a 4 coefficient instead of 2. So if we multiply the whole thing by 2, that will give us 2 HFs times 2. We will get 4 HFs total in the overall reaction. So this works just like algebra, just like basic math. If you multiply one thing by 2, you have to multiply both sides by 2. So let's write that second reaction now. So we're going to have our H2 gas plus our F2 gives us, now remember, we multiplied by 2, so 4 HF, and again, we multiply by 2, so we need those coefficients. Okay, so now we have the HF. We have that, because remember, we're going to add all these up. In the very end, we're going to add them up. Okay, so now we still need this CF4. So, looking at our center reaction, it appears we could use that. However, we do need 2 CF4s. Okay, tetrafluorocarbon. I'm not really sure. CF4. I'm not really sure the exact name, but we do need 4 of them, right? We do need 2 of them. In our subcomponent reaction, we only have 1. So if we multiply the center reaction by 2, and that will give us 2 CF4s, which is what we need. So I'm going to write that reaction multiplying by 2. Okay. Okay, so finally we get to the last step. Okay, we have some CF4. Do we have 6F2? Well, we have 4 in the third reaction. We have 2 in the second reaction, so that makes 6. So you'll notice that we have all of the species present in order to match the overall reaction. So let's add this just to be sure. So again, this works like algebra, where if you have two things on both sides of the equal sign, then you can cancel them out. So 4x plus 2 equals x plus 6. You can combine like terms. So so let's write that overall equation first to show you how that works. So I'm going to try to fit it all on here. I'm going to leave out the phases just so I can fit everything. So again, I'm writing all of my component parts. Yes, the third reaction. Okay, so now we have okay. So now you've seen that we've just combined, we've added everything on the reactant side, we've added everything on the product side, and we've written the reactions below. So now we can combine like terms. So you'll see we have 2 F2s, 4 F2s. So we can rewrite that. To get 6 F2. Okay, so now we've just combined these F2s together to get 6 of them. So now we look for things on either side that we can cancel that are the same. So 2 carbons are the same. 2 hydrogen gases are the same. Is there anything else? And the answer is no, there's not. So rewriting that reaction again, the overall reaction with everything crossed out that we just did before. Let's see if that matches. So C2H4 plus 6F2. That we have. Good. Gives us 4HF plus 2CF4. That we have. So as you can see, we built up 3 subreactions to equal the total reaction. Now we need to figure out what to do with the delta H values. So delta H for the reaction is going to equal, we're looking at our 3 delta H values of our components. What do we do to the first equation, to the first reaction? We multiplied it by 2. You can see that listed as our second reaction. So that means that we're going to take 2 times negative 680 plus, again we took 2 times this second component reaction with the carbon and the F2. We multiplied that by 2. So again, we're going to multiply that delta H value by 2. And the last one, we inverted the reaction. So we're going to add a negative delta H value. And I'm just going to erase this just a little bit. Okay, so we multiplied the first delta H value by 2 and the second delta H value by 2. And the third reaction, we simply inverted. So therefore, we make the delta H value have the opposite sign, which in this case, it would go to a negative sign. So we add these all together. And we get negative 2,486.3 kilojoules. And that's how you do Hess's law. One thing to keep in mind is that the hardest Hess's law problems are done just like the easiest, meaning you could have up to 5 subcomponent reactions. Okay? And each reaction may have the same reactant or product many times. So in all 5 reactions, you could have 3 reactions which all contain CO2, for example. But you want to keep in mind that the key takeaway is that you're going to eventually cross out things that appear on either side. So in the end, it doesn't matter whether you have a species listed multiple times, as long as they cross out and as long as they cross out to produce the overall reaction that you're trying to find, then that's okay. Whoops. Okay, thanks for watching. See you in the next video.